estimating the proportion of the population, like that. So about the statistic and related to the parameter that you are trying to guessing it. So that type of the guessing is generally called an estimation. Generally, you are expressing as the expected value of statistic is equal to the parameter. So that is what we are going to use in the uh, estimation part. And pen and Microsoft Whiteboard. Now, so in this estimation, we are mainly having the two types. One is called point estimation, and the other one is called interval estimation. Point estimation is we are guessing the value of the parameter exactly based upon the statistic. For example, suppose you have written the an examination which is in objective model. So based upon the objective model, because only it is a multiple choice answers, uh, if the key is given, then you can estimate your mark, or based upon the material that what you are having, you can estimate your mark based upon the what you have written and what is an exact answers for those, and you can perfectly or exactly estimate your mark. So that is comes under the point estimation. I will get uh, 42 marks out of the 50. I will get around 75 marks or 80 bits are correct out of the 100. So which is always a point estimation. Generally, it may not much differ it also. And in some situations, suppose if it is a descriptive type, then if it is a 10 marks question or 20 marks question, then depends upon the value. It may be the variation may be existing from plus or minus 5 or plus or minus 10. So what you are guessing, you may get the more mark or less mark of the some variation may be existing. So in that case that you are giving some an interval base, I may get in between 60 to 70 marks. So like that you are guessing, which is generally called an interval estimation. And generally whenever you are giving this interval estimation also, that how much confidence that I'm having, I may get in between 60 to 70 marks with a confidence of 99%. So the confidence level is also counted at here. But in the point estimation, it is always an 100%. And we are pinpointing it. That is the major difference between the point estimation and interval estimation. And most of the sample studies depends upon the cases. We are going to use the confidence interval estimations. So how much confidence that you are having it. So that is also what is the allowable error that you are defining it. In that case that I am defining another terminology called an hypothesis. I think all of you know the hypothesis, but it is a prerequisite. Just I am redefining. Hypothesis is any statement or assertion or assumption about a population or its probability distribution or on its parameters is said to be a statistical hypothesis. Simply we are calling as hypothesis. Any statement or proposition. Proposition means which we can classify into either true or false. This statement must be on the population or on its probability distribution or on its parameters. So such a statement or as a statement or proposition is generally called a statistical hypothesis. So these hypotheses are generally we can express in two ways. One is called simple hypothesis and other one is called composite hypothesis. Simple means we are exactly specifying the values for the parameter. So that is called a simple hypothesis. Let's suppose if I am specifying that this particular class average mark is 80. So the average mark of the class is 80, pinpointing it. So the pointed out the value. So mu is equal to 70. So the value is parameter is specified, therefore it is called simple. Suppose if I am not specifying exactly, this class is above 70. Above 70 means it may be 75 or maybe 80 or 90 or 100, that we are not exactly specifying. Such type of the hypotheses are called the composite hypothesis. Whether the statement may be correct or may be wrong, so the way of the expression that you are calling as simple and composite. And the another is null hypothesis and alternative hypothesis. So hypothesis generally whenever you are writing and to test the hypothesis, we are expressing in the two ways. One is called null hypothesis. So the null hypothesis is generally defined as the possible rejection of a true hypothesis, which is hypothesis that is assumed to be true, that is called a null hypothesis. So possible rejection of a true hypothesis is called null hypothesis. That means what the statement that you are assuming it is true, you are most likeliness or favorableness about the statement which is correct. That statement only we have to consider as null hypothesis. And what is the complementary statement to that? Such hypothesis is generally said to be an alternative hypothesis. So some of the examples for simple null hypothesis. If I am assuming that this class average mark is 75, I am assuming that it is a true. So take it as a null hypothesis. So we are expressing as H naught, mu is equal to 75, where mu is nothing but the mean of the population. And what is the complementary statement to this statement? So this class is above 75 or below 75, or I'm not specifying it, not equal to 75. So these are the three complementary statement to equal to 75. Those are generally said to be alternative hypothesis. The alternative hypotheses are generally denoted with H1. Okay, and the another one that what you are using is uh, types of errors. So the types of errors that we are having, one is called the type 1 error and type 2 error. So what is the type 1 error and type 2 error is? Already that I told any hypothesis that you have taken, that hypothesis we are having two situations. One is called the hypothesis is the true, and the other possibility is the hypothesis is not true. So based upon this, we are accepting the hypothesis or we are rejecting the hypothesis. If we are accepting the hypothesis, so that is one possibility, that is called one situation. Rejecting the hypothesis is another situation. And also we are having two types of the actions. So the actions are, we are accepting the hypothesis or we are rejecting the hypothesis. Now, if we are having the hypothesis, yes, just 1 minute, I will open the
Is there any issue, sir?
Did he leave? Just see. Is he there in the corner? Is there? Is there?
Sir, Batra Chalu, sir, can you hear me? Sir, your microphone is muted, sir. Once time. Your microphone is muted, sir. Sir, is everything okay, sir?
Make home for him.
hello. Yeah, screen is whiteboard is visible to you.
Yes, sir. Yes, sir.
Okay. Now, uh, let's suppose here I'm giving one of the table. Okay. Now, this is let's suppose the H naught is one statement. The mean of the population equal to 75. So this statement may be correct or may be wrong. So this is H naught true and H naught is not true. There are two situations are there. And similarly, based upon that we are rejecting the statement or we are accepting the statement. H naught. Okay. Now suppose the statement is true, and if you have rejected the statement, so is the decision is correct or wrong? So the decision is wrong because the hypothesis is correct, but we have rejected it. So this is called one type of the error. Similarly, suppose if decision is wrong, so because it is a true statement is rejected, and the false statement is rejected, the decision is correct. And here also the statement is true and accept the statement. So whatever the decision that you are taking, that is correct. Suppose the statement, the H naught is not true, then if you have rejected the statement, the decision that what you are taking is also not correct. So the decision is not correct in two situations. So one is we are rejecting a true statement or accepting a false statement. So this is generally said to be a type 1 error, and this is generally said to be a type 2 error. So the type 1 error is uh, reject H naught when H naught is true, and the type 2 error is accept H naught when H naught is not true. The probability for the chance for occurring the type 1 error is generally called level of significance. Level of significance. This is only we are indicating with alpha. And most generally we are going to use p-value. So this is the p-value that what you are examining. And the probability for type 2 error is generally said to be or denoted with beta. And 1 minus beta complementary value, if you are writing, that is called the power of the test. So the complementary probability of the type 2 error is called the power of the test. And the probability of type 1 error is called the level of significance. So type 1 error is reject H naught when H naught is true. So in most of the situations that you are going to use, this is a basic foundation for the hypothesis. So what is the null hypothesis? The situations for the hypothesis. So these are the two situations, true and not true, and we are accepting and rejecting. So these are the action that you are taking it. So based upon that you are taking the decisions, the decision is correct, not correct in the two situations. Now the question is, out of the two errors, these two errors to be minimized, but we cannot minimize the two errors simultaneously. Therefore, we are trying to fix one error at the lowest level and trying to minimize the second type of the error. So we cannot minimize the two errors, type 1 and type 2 errors simultaneously. Therefore, we are trying to fix one error at the lowest level, which is more dangerous. Then you are trying to minimize the second error. So such a theory is generally said to be Nyman-Pearson theory. Nyman-Pearson theory. So that's why we are fixing the alpha value first. We are fixing the alpha value first. Okay. Now, now I'm coming to the uh, part of level of significance and power of the test. So test procedure, all of you know. So whenever you are going for any of the tests, generally the first step is we have to frame the null hypothesis. The next step is we have to frame the alternative hypothesis. The next we have to identify whether it is a one-sided hypothesis or a two-sided hypothesis, or the next we have to choose the alpha value, and the next that you have to identify the appropriate test statistic, what is the suitable test for the given hypothesis to be tested, and we are evaluating the values, that is called, we are calculating the value, and the next we are choosing the uh, critical value, and so once that you have chosen the critical value, then that is the whatever, this is always the critical value that is collected from the statistical tables. Then we are comparing the calculated value with the tabular value or the p value, and we are taking the decision, so shall we have to accept or reject. So this is generally said to be a test procedure, that what you are going to use. Okay. Now, uh, we are having the so many tests are there. So the small sample test and large sample test, and T, F, and chi-square. But whatever the tests, the our analysis of variance is comes under the F test. Okay. Now, this is one of the table form that I am giving in a general way. I want to test the mean of the population. So whether it we are based upon a single sample or two samples, and we are the hypothesis to be tested, the mean of the population is equal to a particular value or not equal. Generally, you are going to use a t-test, and if it is a two sample, then you are going to use the equality of the means. That is also another test is there, whether it is a paid or unpaid, or related or unrelated samples. Okay, we are going to use the t-test. Now suppose if I want to test more than two samples, the means are equal or not. That is h not equal to mean of the several means. So in that case, we are going to use this is F test, which is nothing but analysis of variance. So analysis of variance is used if we are having more than two groups and all groups means are equal or not. For testing, generally you are going to use the F test or analysis of variance. There are a different type of the F tests are there, but specifically here I am specifying it. Okay. Testing of the variance is also an F test, but the ordinary analysis of variance is only the equality of the means of several populations. Okay. And also we are going to use one of the basic theorem that is called Gas-Markov theorem, and which is based upon the foundation for the analysis of variance and for the evaluation of the degrees of the freedom. We are going to use the Cochrane's theorem, but I'm not going in much detail because I'm explaining with the problem solution itself, because it is very difficult for you to understand the statement of the theorem also. That's why I'm skipping that part. Now, the analysis of variance. Analysis of variance is a technique which is used for the separation of variance from one group of causes to another group of causes. That means we are having the total population observations. I'm dividing the populations into different groups, like homogeneous groups. Then I'm trying to find out what is the total variation of all the observations. That variation that I'm splitting into, what is the variation of different groups and what is the variation between the groups, because the total observations, the variation that I am keeping at one part. Now our total observations, again now I am dividing into different groups. So once that you are divided based upon some particular criteria like homogeneity, based upon some characteristic, then within the group what is the variation, and between the groups what is the variation. So total variation is divided into two or more parts, depends upon the situations. Such type of the separation of the variance from one group of causes to the another group of causes, which is called analysis of variance. Just like splitting of the total variance into two or more parts, which is called analysis of variance. So in the analysis of variance, we are having many techniques are there for the univariate case or for the multivariate case, and also based upon the statistical model that you are going to use, whether it is a fixed effect model or a random effect model. So based upon that, we are calling as an ordinary analysis of variance or variance component analysis. And also there is another part in the analysis of variance. Along with the observation, there is some another independent variable is also observed in those cases that you are going for analysis of covariance. So these are the major four parts of the analysis of variances. Analysis of variance of univariate, analysis of variance for multivariate, analysis of variance for random components called variance component analysis, analysis of variance if some covariate is also observed, that is called analysis of covariance. Okay, so these are all called analysis of variance techniques. Now coming to only the analysis of variance of univariate only, then analysis of variance one-way classification, analysis of variance two-way classification, and two-way classification with only one observation per cell, with interaction or without interactions, or m observations per cell with interaction and without interaction. M observations means equal number of observations per cell or unequal number of observations per cell. So these are all the different possibilities. And analysis of variance, maybe some three-way classification or four-way classification and you can generalize to some KV classification. Okay, so these are all the simple univariate analysis of variance, the number of analysis of variance techniques that are available. You can adopt these techniques for the different type of the designs. Okay, now coming to one particular part, the same that what I have given in a classification table format of analysis of variance, one way, two way, three way, so on, k way, and two way, one observation per cell or equal number of observations per cell, that is more than one but equal, and unequal number of observations per cell. So whether it is one observation cell, generally we are not going for with interactions much, but with the factor that you are going to study the with interaction, and m observations per cell with and without interactions, either unequal also with interaction and without interaction. The same that what you can use for the three-way and also for k-way. Okay. Now, the variance component analysis is, suppose if you are taking the model like let's suppose the observation is like Yij is the observation, which is equal to some average value plus some effect value and some random error. So this is an error which is involved in the observation measurement, and actually the value must be this one, and there is some effect due to a particular treatment that is applied, so that effect is alpha I. Now this effect is if you are saying that it is a fixed effect, then only we have to call as analysis of variance. Suppose the effect is random, which is not a fixed one, then generally you are calling as a variance component analysis. So fixed effect, random effect. So whenever it is fixed effect, the hypothesis that what you are writing is mean of the first group is equal to the mean of the second group, equal to so on, the mean of the kth group. And against the alternative hypothesis, the means of the groups are not equal. At least some are differ. Okay. So the same thing that also you can write the effect of the first group and second group, so on the kth group. The value will be 0. If all value effect, there is no effect, then the means values are always equal. And error is always a random component only. And the errors are generally follows a normal distribution with mean is 0 and variance is some sigma square. Even if the YIJs are follows, observations are follows a normal distribution with mean is mu and variance is sigma square. So the average of the observations of the population is mu. That's why I'm writing this one. And there is some effect due to the ith treatment. That's why it is called alpha I. If the effect is 0, then automatically the means are all equal. And alternative hypothesis is at least some alpha I and j are not equal. Okay, so this is reflecting of this part. And if the alpha I values are all 0, that is called a fixed effect model. If the alpha i's are random, if the random, then you cannot say that the values are zeros. So, which are totally is different. In those cases, the hypothesis to be tested will be like this. So, H naught will be the variance of the first group is equal to the variance of the second group is equal to so on the variance of the kth group. So, this is only to be tested in the analysis of variance. And that type of the analysis of variance is generally called variance component analysis. So this is when if alpha I is random, the effect of the ith treatment is random, then we have to go for, we have to call the analysis of variance as variance component analysis. That is total variance. We are dividing into different components. That is also nothing but simply analysis of variance only. Okay, but alpha is random, then only we are using a different terminology for better understand bifurcation. Now, so the same, the variance component analysis is the technique of partitioning the total variation into two or more components such that the effects in the model are random effects or combination of random and fixed effects. So if it is a fixed also, some are random, some are fixed. If it is a two-way classification or three-way classification like that, some are random, some are fixed. So then it is called a mixed effect model. Okay. So in that also one-way classification and two-way classification for the we can evaluate um, for the balanced data and also unbalanced data. And analysis of covariance. So which is also a technique that what we are going to use. It is possible to observe the response variable y along with another independent variable x, which is linearly related with y. The variable x cannot be controlled by the experimenter, but can be observed along with y, which is called a covariate. So in that type of the cases, we are whatever the analysis of variance that you are calculating, that is called analysis of covariance. So analysis of covariance is the method of adjusting the effects of uncontrollable, the nuisance variables to the response due to the treatments and the linear effect of the response variable with a concomitant, that is called a covariate. Concomitant variable is nothing but a covariate. If such an adjustment is not performed, the concomitant variable could inflate the error mean square value, that is called the variance, make true differences in the response due to the treatments which are harder to detect. So, which is another concept that what you are going. So, in this also you can go for the one-way classification, two-way classification, and also m-way classifications. Now, I'm coming to analysis of variance one-way classification. So, what is analysis of variance one-way classification? So, analysis of variance one-way classification, the data, whatever the experiment that you have conducted, we have to express the data or present the data in this particular format. So the format that what we are presenting is this one. Let's suppose we are having totally n observations are there. I am dividing the total n observations into some k groups. So each group is as homogeneous as possible. That means similar observations are one group. So these are all similar observations. Maybe some slight differences are there in the observations, and so homogeneous. Or this is a one particular class. Suppose in a paddy crop that I applied one particular drug, or I'm taking a set of patients. So I'm giving a dosage of particular drug with a particular dosage. So that is dosage A. And second, high dosage that I had given, and these members. So what is the effect? And different dosages that I'm giving it. What is the effect? So all those are studied in this simultaneously. And I'm not giving to only one member, so I'm giving. So it depends upon the availability. So first group, I'm taking the same patients, but I'm giving the different dosages. And for the first set that I'm using some 5 members, second set that I'm using 10 members, maybe third set that I'm using 2 members only. That is depends upon the availability. So that's why it may be some unequal. So such type of the whatever the experiment that you have conducted, and if it is possible to express only one category, we can divide that into different groups based upon some particular criteria. Then we can go for the one-way classification. And the hypothesis that what we are testing is only one hypothesis. What the hypothesis is? All groups means are equal or not. That is what we are going to test. So H0 is only one hypothesis is tested. And the statistical model that what we are going to use is Yij, that is observation, equal to the mean plus the effect of the ith treatment plus the random error. So the Yij is the jth observation under the ith treatment, and mu is the overall mean, alpha is the effect of the ith treatment, and epsilon ij is the random error associated with Yij. Now assume that the observations are independent and there follows a normal distribution, and with the mean is mu and variance is sigma square. Then the hypothesis that what we are testing is also this or the assumption. The observations are random, independent, and follows a normal distribution. With the mean is mu and variance is sigma square. And the errors are random, which are independent and follows a normal distribution. With mean is 0 and variance is sigma square. All the effects are additive in nature. So either whatever the effects, environmental effect or the treatment effect, it may be some other effects, all are can be added, which will give the total effects. So and linearly connected. Now H0 mu1 equal to mu2 is equal. So this is what is the all group means are equal or not. But what you are going to test, this is nothing but the effect of the treatments. So all are equal. Okay. So maybe 0 or fixed. So most of the cases that what you are considering, the alpha is are zeros. So then automatically the values will be same. Okay. Now the model, this also you can express in a matrix form or a general linear model. Y is equal to x beta plus epsilon. So these are the observations, and this is the sample design matrix, and this is a vector of the parameters, and this is the vector of the errors. Okay, and we can estimate the parameters, and because this is a theoretical derivation, which is somewhat maybe some difficult for you for understanding. Now here I'm dividing the total variance or into two parts. This is one variation. This is generally said to be between groups and called treatment sum of squares or between groups, and this is within group. Within groups variation, between group variation. So total variation is splitted. Okay. Now, how to evaluate the values? So simple procedure I am giving manually you can evaluate. I will explain with the numerical problem also. First step is compute the totals for each of the treatment. Okay, like if you are having the data like this, so whatever the observations are there, compute the totals for each group or each class. Then compute the grand total, sum of the totals, sum of the totals. So first I am calculating the totals of each class, then totals of the totals. So that is called a grand total. Okay, and then I am calculating the correction factor. The correction factor is generally calculated the grand total square by total number of observations, where capital N is the total number of observations. Then compute the raw sum of squares. Raw sum of squares is you square each observation and add. That is called raw sum of squares. So y11 square plus y12 square plus y13 square, so on y1n1 square plus y21 square, y22 square, so on. Last ynk square. So sum of all each observation that you square it and add it. That is called raw sum of squares. Then compute the total sum of squares. Total sum of squares is equal to raw sum of squares value minus correction factor value. That is called total sum of squares. Then evaluate the treatment sum of squares. So treatment sum of squares is equal to you square each of the class total by the number of observations in that particular class. So first class only 2 observations are there. That total square by 2. Suppose second class total is T2, then T2 square by, in the second class if there are 10 observations are there, then T2 square by 10. Okay, like that. Minus correction factor. Then calculate the error sum of squares. So error sum of squares is total sum of squares minus treatment sum of squares. So which is called the uh, error sum of squares value. So RSS, then you, whatever the values that you have evaluated, you express in a tabular form like this. So first column is containing some source or source of variation. That is, what is the total variation and which is divided into two parts. This is called between groups and within group. Between groups or between classes and within classes. Within classes is generally called error. And whatever the treatment SS, the summation of Ti square by Ni minus correction factor, that's what I'm presenting it here. And whatever the total sum of squares, RSS minus correction factor, you can express it here. And this value minus this value, RSS minus correction factor minus this value. So which is, that is called error sum of squares value. Okay. So total SS minus treatment SS. And so totally if you are having n observations minus 1. And how many classes that you are having? K classes minus 1. And n minus 1 minus of k minus 1. That is nothing but n minus k. Then sum of squares by its degrees of freedom that you calculate, that is st square. And sum of squares by its whatever by subtraction by n minus k, so st square. Okay, st square and st square. So these are the, and then compute the variance ratio st square by st square. Okay, so this is the computing of analysis of variance table. Now I will go for, this is one of the data. Let us consider a data resulting from an experiment on different diets A, B, C, D, fed on same types of the rabbits. So I have taken a particular rabbit of a similar weight almost, and had given some feed, different diets. So diets are A diet, B diet, and C diet, and D diet. Then after some time, after feeding of this, that had taken the weights of the rabbits. So the weights of the rabbits on first diet, I taken 4 rats. Second diet is also given to 4 rabbits of different, and third diet is also given to another some set of 4 rabbits, and so on. And the weights are measured after some time, after feeding of a particular diet, some 10 days or 15 days. So these are the observations are given. Now I want to test the average weight is same or not. That means due to diets, there is no change in the weight. That's what I want to test it here. So here there are 4 rats that I had taken and 4 diets that I had taken. So totally I'm having 16 observations and the treatment total. So what is the total of first diet, second diet, third diet, and fourth diet? So what is this total? That is TA, TB, TC, TD. Okay. Then compute the totals of these totals. That is 1, 2, 1, 0, 2, 0. Okay. Next, I'm calculating the correction factor. So correction factor is square of the grand total by total number of observations. Then compute the total sum of squares. For that, I'm computing the raw sum of squares first. Raw sum of squares is nothing but square each observation. So what are the observations? First observation 62 square. Second observation 63 square. 4, 68 square. 56 square. 60 square. 67 square. 66 square. And 62 square. And so on. 63 and so on, 61 square. So each observation that you are squaring and adding it, that is called raw sum of squares actually. Minus correction factor. So the resulting value is 275. Then here also I calculated another one, 244 square by 4. First diet A total. Okay, so 2 whatever this total, okay, that is 244 square by how many observations? 4 observations. Like that I calculated it here. Second total, third group total, fourth group class total. Okay, and minus correction factor, which is equal to this. Then I'm calculating the error sum of squares, which is total sum of squares minus treatment sum of squares. Total is 255 and treatment is 191. So if you calculated, you get the rest value is um, then I'm evaluating, I'm expressing these values in a tabular form. So total SS 60, so that I'm placing it here. 0038 that I'm placing corresponding to treatment. This is total. Okay. But sorry, not express this one. Yeah. Uh, so 275 and 191 and 83. Okay, and there are totally 16 observations are there. So 16 minus 1. And 4 classes are there. So 4 minus 1. And 15 minus 3, that is 12. Then sum of squares by its degrees of freedom, which will give the mean square. And similarly for the second one. So 83.5 by 12. So you will get 6.95. After computing of this 63, this value by 6.99, you will get variance ratio. This is called an F, and this is follows an F distribution. So you have to use F table for this. Okay, and whatever the critical value that you have to table value that you have to see and compare this calculate 9.17 with the table value and whether we have to accept or reject. So whenever you are seeing the table also 3, 12. So with the corresponding degrees of freedom only that you have to examine. Now coming to the two-way classification. So let us whenever we are considering the two-way classification, which is an extension, but there are two possibilities are there. We can classify the data. One way is with respect to classes, and another one is with respect to another factor. So that's why I am calling as a factor A and factor P. Okay. So maybe some M factors in the case of the M-way classification. Now, uh, these are the different observations are there. The same type of the model that I'm going to use. So this is alpha is the effect due to the ith class, that is row wise, let's suppose, and beta j, which I'm considering or studying corresponding to the column, therefore which is the beta j. Okay, so and assume that the same assumptions, observations are follows normal distribution with the mean is mu and variance is some sigma square, and alpha I is the random error. Whatever the mean value will be 0 and variance is sigma square. So these are the assumptions. Observations are random, observations are independent, normal distribution, mean mu and variance is sigma square. And errors are also follows normal with mean 0 and variance is some sigma square. And the hypothesis that what we are testing are two hypotheses. One is we are dividing the data in row wise, and also the another one column wise. So row effects are zeros and column effects are also zeros. That means due to factor A, the effect is 0, or due to factor B also, the effects are zeros or not. That's what we are going to test. And this is the statistical analysis where, so which is a theoretical expression, only the major step that I have written. And total sum of squares is split into two parts. One is called due to factor A and due to factor B, and the rest is called an errata. Now, we can evaluate the two-way classification like this. So you calculate the totals for each row called R1, R2, R3, so on, Rk, and also calculate the total corresponding to each factor of B. That is also called the column totals, C1, C2, so on, some Cn. Then compute the grand total. So grand total is sum of the row totals or column totals, any one that you can use it, which is gives the grand total, which is G. And compute the correction factor, so which is equal to G square by N, and compute the RAM sum of squares, whatever the raw sum of squares is nothing what you are squaring each observation and adding it. Then compute the total sum of squares, which is equal to the raw sum of squares value minus correction factor. And treatment sum of squares due to whatever the evidence, whether it is due to factor A or due to factor B. So whenever you are going for due to factor A or due to factor B, due to factor A or due to factor B, so which is always the same. Okay. Then you can go for the column totals. So one is generally on treatment wise I written it here, but you can consider one for the row effect studies, and the other one is for the column effect or factor A and factor B studies. So rows summation of Ri square by n minus correction factor, and columns minus k by correction factor. And the error sum of squares, which is equal to total SS minus treatment SS minus block SS. Okay, so this is what you are going to use. And the same thing that you are trying to express in a tabular form, like this is the total sum of squares and factor A sum of squares value and factor B sum of squares value, and this total minus sum of these two, you will get by subtraction, you will get the error sum of squares. And corresponding to the degrees of freedom, total number of observations minus 1, and total number of classes due to factor A, total number of classes due to factor B minus 1. And sum of squares by its degrees of freedom for calculating, you will get mean square value. Okay. So example on the same that. So this is the table. I am calculating the row totals and also the column totals. And these are the row totals and column totals, grand total. Okay. And calculating the correction factor, grand total square by total number of observations, and you raw sum of squares each observation that you square it and add it minus correction factor, and whatever the factor A, whatever the R1 square plus R2 square plus R3 square, so on, by the number of observations in each row, and minus correction factor. Similarly, corresponding to the column. So whatever the column totals are there, and some value that by number of observations in each column minus correction factor. And the error sum of squares, which is equal to the total value, total sum of squares minus due to factor A due to factor B, which is equal to F. So the same thing, that whatever the values that I am expressing it here. So total corresponding total value, and due to factor A 0.38 whatever the value, and 0.0015 that, and whatever the subtracted value here at the time. And in factor A there are three classes are there, therefore uh, therefore 2, and factor B there are 5 classes are there, so 5 minus 1, and totally there are 15 minus 1, that is 14. Error is 8. Okay, so mean square is for this one. So this is a sum of squares by its degrees of freedom, that what you are going to use, which is nothing but sum of squares by its degrees of freedom, that is called mean square. And then compute the variance ratios. So variance ratio, then compute the effect. Okay, so this is the way of the computing the two-way analysis of variance. Similarly, that you can evaluate for m observations per cell also. Let's suppose we are having n observations per cell, then this is a general the way of the data. This is called m observations per cell, not one observation, only two observations, m observations per cell. So two-way classification, so factor A and factor B, row wise and column wise, but in each cell there are m observations per cell. Okay, so for this also you can carry out the analysis with the interaction effect, and generally mostly that you are going for the one-way classification and two-way classification, and the m-way classification that you are not going to use much. Okay, and with interaction also that you can evaluate. This is the general the computational procedure for the same whenever you are going for the interaction effect. So compute the row totals and column totals and compute the grand total, then compute the correction factor, then compute the raw sum of squares, that is sum of squares of each observation, and then compute the total sum of squares. Total sum of squares is equal to the raw sum of squares minus correction factor, then compute the treatment sum of squares, so which is equal to whatever the squares of each of the row totals by the number of observations in that row minus correction factor. And similarly, this is corresponding to factor A and corresponding to factor B, that is called another treatment that what we are going to use, that is called a column, that is summation of Cj square by K minus correction factor. Then compute the interaction sum of squares, so that is that what I have written, and then compute the error sum of squares, so total sum of squares minus treatment minus blocks, so which is gives the error sum of squares. Okay, so this is the what we are whatever the value that you are going to present in the tabular form: treatment sum of squares, block sum of squares, interaction sum of squares, and error sum of squares, and total. And the degrees of freedoms are also that I expressed the same. Then sum of squares by its degrees of freedom, which will provides the mean square value. Then compute the variance ratio. Okay, so this is what we are going to present it. So the same that what I am presenting it here. In each cell there are 4 observations are there. So that what I have presented it here. In the study of extracting and concentrating the proteins of one of the seeds in livestock feeding in one of the place of Nigeria to eliminate the toxic substances from the seeds. The following are the effects of the extraction time, which are in minutes, that are expressed as 30, 60, 90, and 120. Okay. Uh, the the and floor to solvent ratio on protein extractability in the percentages also the of the seeds that are also given. Now the data that I'm trying to express in the two-way model, and we are trying to analyze based upon applying the two-way classification with m observations per cell. Okay, so 4 observations per cell. And what about the data that you are trying to express? I have not calculated it here. So this is a table, and whatever the formula that I had given. So according to this, that you have to evaluate and you have to present in this table. And similarly, that you can go for the analysis of covariances, one-way classification or two-way classification. What is analysis of covariance? Here, let analysis of covariance uh, is just like what I had told. Along with the original response, there is another independent variable which is also observed. So that is generally called a covariate or concomitant variable. Let Yij be the observed response and Xij be the corresponding observed covariate value corresponding to ith treatment, that is when applied in the jth block. And assume the responses are Yij and Xij, then assume that these are follows the normal distribution with the mean values. Yij mean is mu y and variance is sigma y square, and similarly Xij's are follows normal distribution with the mean is mu x and variance is some sigma x square. And whatever these values, that again I'm responsive that I'm trying to express in the tabular form like this. So these are the V treatments are there, and B blocks, and I'm trying. Not only it is just like a two-way classification. You can also express in one-way classification also. First treatment, second treatment, third treatment, so on, Bth treatment. There is no concept of the blocks also. In that case, maybe some unequal observations, just like simply analysis of variance one-way classification. Okay. And this is a two-way classification with more number of observations per cell, or multivariate case. In the multivariate case also the same, that what are many observations simultaneously that you are going to study at here. Okay, so this is the way different the analysis of variances that you are going to evaluate. So we can concentrate about the major is the one-way classification and two-way classifications. Actually, this analysis of variance, one-way classification, and concept of the analysis of variance, which was introduced by R.A. Fisher when he is studying his graduation itself at the age of 19th year. In 1914, he introduced the concept of the analysis of variance. Okay. He is one of the, he's the father of statistics, R.A. Fisher, so who introduced this analysis of variance concept. And this analysis of variance concept is a major foundation for the design and analysis of experiments, and also that you are applying in many other fields. Okay. So now if you are having any of the questions about, and once the analysis of variance is completed, then also you are going for some post hoc tests. This is also part of the analysis of variances. So in the post hoc tests, now generally, suppose for whatever the data that I evaluated analysis of variance one-way classification or two-way classification, and the hypothesis is rejected. So hypothesis rejected means all groups means are not equal. That means some groups means are equal, some groups are not equal, let's suppose. Then due to which group the hypothesis is rejected, that I want to know it. So particular part that I want to isolate it. So in that type of the situations, generally are going for post hoc tests. That is after the analysis of variance is conducted, if the hypothesis is rejected, then only you have to go for this post hoc tests. Suppose the hypothesis is accepted, there is no necessity for going for this post hoc tests. There are many post hoc tests are there. Almost all the post hoc tests are simply based on a t-test with a slight modifications. These post hoc tests are, one is Fisher's least significant digit test called LSD test. LSD test. You can apply Tukey's t-test, or you can apply Sheffy's t-test, or there is Duncan's multiple range test, DMR test, generally what we are calling it. Or you can use Born-Ferroni's test, or you can use Newman Hewlett's test. So that you are having there are a number of the post hoc tests that are available. You can apply any one or two, that's enough. One is enough, no need to go. And most of the cases you are going for either DMR tests or LSD tests. In some of them, they are preferring Sheffy's. Most of the nutrition tests are biological. In all the experiments, you can find out the first four tests. Rarely that you are applying the other tests like Baronis or Newman Hewlett's test or some other. Okay, and these are, we are applying some particular two groups for every pair that you have to evaluate, apply the test statistic, and we have to examine whether the value is a significant value or insignificant. So based upon that, due to which group it is the hypothesis rejected, that you are trying to identify. Just like it is, suppose if you are having whatever the paddy, that is some paddies are available on rice, then you have to identify uh, by each one separately and keeping aside. So for that type of the part that you generally whatever this post hoc test, that what you are going to use. Okay, and the general the test statistic formula that what you are going for any of the post hoc test is the difference of the groups means by 2 by n into the mean square error, that what you are going to use. That means whatever the analysis of variance corresponding to error in the mean square column, whatever the value is there. So whatever the mean square error, this value 6.95. So this is what you are going to use at here. Okay. So whatever the mean of the first group minus mean of the second group by square root of 2 into whatever the mean square error by number of observations in that particular group. Okay. So this is what you are going to use for the general formula for the either LSD or Tukey's or Sheffy's, but slightly formulas may be differing for one to the another. Now generally we are going to use the statistical softwares for evaluating of the analysis of variance one-way classification or two-way classification or post-hoc tests. By the next session that I will show the implementation of this one for the some of the completely randomized tests and randomized block tests or Latin square tests. So which are just simply completely randomized test is nothing but the one-way classification, and randomized block is almost a two-way classification, and lattice square is the three-way classification, and factorial experiments, which is a two-way classification with interaction effects like that. So in those experiments that I will give the how to use evaluate of these values by using some statistical software. So mostly that I will use the either SPSS or R, so whichever that you require. So with those that I will demonstrate the same thing. Now, if you are having any of the doubts or clarifications, you can ask now, please. So it is open for the discussions.
Thank you, sir. Participants, if you have any questions, you can ask.
Either the concept of the analysis of variances.
Kindly unmute yourself and you can ask participants, or you can text to the chat box as well. We are looking for the we are seeing the chat.
Yeah, okay. You can also ask this. Chat box.
Good morning, sir.
Type it and,
can you hear me, sir? Good morning.
Yeah, good morning.
We can hear you.
Yes,
Good
I'm
morning.
Dr. Sunita. Sir, can you hear me, sir?
Yes, madam.
Yes, ma'am.
Yes,
We can
thank
hear
you
you.
very much, sir. You have given all the basics for the analysis, for how to do the statistical analysis, all these things in a manual way. Sir, are you even going to show us using the design of expert with simple designs like 2 square or 3 square or even Higuchi? Can you please help us to do the analysis using these designs? And especially I want interpretation of the analysis, as well as if the trial is not giving the required data, how to increase the number of trials. So these things I want to learn, sir.
Okay, but design expert is not a free trial.
Okay.
It is how to. I'm not having the copy of this one. If trial version is there, that I will show it.
Yes, sir. Yes, sir. I have the trial version also, sir.
So otherwise,
yeah.
Okay. So just to give the link that I will show in the whatever third session that I will demonstrate about design expert. Okay. So because the principles of experimental design and that I will explain in the next session. Okay. After the session is over, then whatever all these parts that I will demonstrate in the design experts.
Okay.
So in the design expert that I can show it, and also SPSS, and also in R.